to the local audience, and good morning to Ralf. And I think there might also be many audience stay up at midnight. So this is Rich Yang from Fudan University hosting these summer school lectures. And thank you everyone for being online with us. Before we start, please allow me to briefly introduce Professor Schindler. I think many of you may already be very familiar with Professor Schindler, and at least we have classes reading Professor Schindler's textbook in set theory. So Professor Ralf Schindler obtained his PhD degree at the University of Bonn, co-advised by Peter Kopke and Ronald Jensen. And now he is a full professor of set theory at the University of Minster. Professor Schindler has, I think, made countless contributions to lots of areas in set theory, say the theory of inner models for large cardinals, fine structure theory, and forcing axioms, and many other areas, which I would say those hardcore set theory. And this week, Ralf will bring us a recent result proving Odin's star axiom from kind of strongest forcing axioms. I think it will be a challenging week, and now let's welcome Professor Schindler.
Thank you very much for this very nice introduction. So I feel deeply honored for having been invited by you to do this. Of course, we all would have preferred that we can travel a bit more, but at some point we will be able to travel again, and we will see how to make the best out of it. I want to start, or I'm not going to start yet, but let me say I did not prepare any slides. I will write on my tablet, and I welcome everybody to interrupt me and ask questions, either by just saying something, or you can type it and point me to a question or something. So I want to adjust the speed of my talks to, I want to not lose anybody. So please go ahead and ask questions as we go along. Another thing, just a general thing I wanted to mention is that I'm kind of planning to have the individual talks each day to be fairly independent of each other. So if you think, well, I got lost, or maybe there is always, I'm not really presupposing that you heard the earlier talks to some extent. Okay, so. And also, I will give references. There are a few references on the webpage already, but as we go along, I will give you more detailed references, and always feel free to ask about them. Okay, so this was a few general words I wanted to say in the beginning. Should I just start now, or?
Okay, I think you can just go ahead.
Okay. Okay, so, or maybe I should say that just recently the sad news reached us that Ken Cunin died, and he has been a great set theorist whose work is just present in a lot of things we do, and also actually in what we will be doing. So this is very sad that we lost him. Okay, so let me see how I can, oops. Okay, now, yeah. Okay, so our topic. So the general topic we are going to talk about is basically one of the key questions of set theory. The set theory originated with Georg Cantor, who discovered that there are more real numbers than natural numbers, more real numbers than even algebraic numbers. And then the question arose, how many real numbers are there? Okay, let's see. Oh, and I forgot to say one thing. If there are any technical problems coming up, please interrupt me immediately. I've had in the past sometimes the case that, you know, the internet didn't work anymore or something like that, right? Okay, so Georg Cantor, for one thing, he found a way to make the question I just wrote down precise. Before Cantor, there was no way to even really formally ask such a question. But with Cantor, we now know what it actually means. So he introduced the infinite cardinals, the Alephes, and stated in a slightly more technical way, he showed that the cardinality of the continuum, which is the same as the cardinality of the set of subsets of omega, is bigger than Aleph 0, and the least possible value is Aleph 1. And the question arose whether it's Aleph 1 or whether it's something even bigger. So what we are more precisely, or more specifically, yeah, this always happens. More specifically, what we want to do, I mean, you could say a lot of things about this question. We want to turn to something immediately somewhat more technical, less philosophical. What we want to do is we want to discuss two sets of axioms. Two sets of prominent axioms which not only decide the value of the continuum, but they happen to decide the value of the continuum the same way. Of the continuum, let me just write 2 to the Aleph 0, that's the size of the continuum, the same way. And one family of such axioms is forcing axioms, or I should say strong forcing axioms. I will say, I will introduce all these forcing axioms, and I will do it very slowly, but let me just now briefly drop the names. So the first forcing axioms we saw in history is Martin's axiom. That actually does not decide the size of the continuum, so let me put it in brackets. But then there were introduced stronger forcing axioms, namely the proper forcing axiom, the semi-proper forcing axiom, which turned out to be equivalent to what's called Martin's maximum. And all these things I will introduce, and they all decide that the value of the continuum is Aleph 2, and this is something I actually also plan to prove in order to get familiar with how these forcing axioms work. Okay, so this will be kind of our first topic in some sense, introducing or shooting towards introducing the forcing axioms and see how they work. They are an important sub-area of set theory, and they give a lot of structure theory of the universe of set theory, in particular of the rank initial segments of V, but not only that. They also imply statements about the global universe. Another set of axioms, or this is rather not a set of axioms, it's one axiom. It's what's usually referred to as Woodin's axiom star, or just star. So this is an even more technical axiom, and I will try to give you. I will introduce this axiom very slowly, and we will talk about how it works, why it is interesting, how you get the consistency of this axiom. And the final goal sort of is, I said that these two axioms decide the value of the continuum in the same way. Nowadays, that's not very surprising, because it turned out that actually a slight strengthening of Martin's maximum, something which is called Martin's maximum plus plus, implies star. Okay, so this is a recent result of, or not that recent, a year ago, of David Espro and myself. And this is kind of the final goal, but we will see how it goes. You know, this would be the ambitious goal, but we will see if we make it or if we don't make it. If that is going to happen, then it's going to happen on the last day that I will sketch a proof of why Martin's maximum plus plus implies star. So this is kind of the final goal. So MM double plus is a strengthening of Martin's maximum, and it implies star. Okay. So unfortunately, I didn't find a way to scroll with this whiteboard. So what I have to do is I just open a new whiteboard. Oops, what's going on? Okay, so the motivation, I mean, the motivation for these two sets of axioms is kind of the slogan that you want to maximize, in some sense, the universe of sets, that you want to kind of make it, you know, the idea is it should be a rich structure. Many of you will be familiar with Gödel's constructible universe, which in some sense you can construe as a rich structure. But on the other hand, it's a very slim structure. It is the least model of set theory which is transitive and contains all the ordinals. So it really just contains what kind of the universe of set theory has to contain, in some sense. Okay. When I said it's in some sense also a rich structure, that follows from sigma 1-2 absoluteness, that, you know, if you think of it model theoretically, if you have a model or even a transitive model of your favorite theory, even if it's a very strong theory like ZFZ plus there is a super compact cardinal, something like that. If there is a transitive structure of that, then you also have a transitive structure existing in the constructible universe. But on the other hand, there is a limitation, namely that the constructible universe cannot contain large cardinals. What happened? Oh. It cannot contain large cardinals. It cannot satisfy strong forms of determinacy. So there is a limitation. So the motivation for introducing these sets of axioms is that you want to have something which is richer in that sense as than the constructible universe, that it can have all kinds of large cardinals, and that it's also rich in the sense, well, let me write on the slogan, maximize. You know, that in some sense, if you can consistently think of something to exist, then it's already there. There is a nice slogan by Menachem Magidor, which I think I cited in the abstract, which says that if an object can be imagined to exist, well, you know, you can imagine all kinds of things. So you have to add a proviso. So you have to say in a reasonable way, in some sense, this is vacuous, right? Because so what does it mean in a reasonable way? You cannot make that precise, of course. But we will try to actually formulate principles which make exactly that precise, and these are the principles I wrote down on the earlier slide. Okay. Okay, this was kind of the very general introduction. And now let me tell you what I'm planning to do today. So today we will start out by introducing, you know, the final goal is introducing these sets of axioms and discuss them and see what implications they have and why they might be shed light on what we want to know about the size of the continuum and about the shape of the universe and the structure of the universe. So we have to start out slowly, and it turns out that the concept of a stationary set is something very substantial in set theory. So I want to start out slowly by defining what stationary sets are and the key properties of stationary sets. Then I want to give a brief recap of the technique of forcing, which many of you already saw, I hope. So I have to say that in some sense, I presuppose for my series of talks that you, for sure, that you are familiar with the key concepts of set theory, but also it would be very helpful if you have some experience with forcing. I will try to organize everything in a way that you don't need much else, but forcing might be helpful. But I will recap today what is relevant for us, and then we will start introducing forcing axioms. Oops. So we will start out by introducing the most classical forcing axiom, which is Martin's axiom. And we will derive some consequences of Martin's axiom. And then we are going to introduce, so Martin's axiom related to the class of forcings which have the CCC, the countable chain condition. And this notion of CCC is getting relaxed in the concept of proper forcing, which was introduced by Schindler. So that's a technical term, proper forcing. And there is also something called semi-proper forcing. And then there are stationary set preserving forcings. Okay. And using these concepts, we will be able to formulate the proper forcing axiom, the semi-proper forcing axiom, and Martin's maximum. So this is the plan for today. So not really serious mathematics, but introducing the key concepts. And as I said, please feel free to interrupt me with questions if you have some kind of background questions. Okay. Okay. Okay, so the first topic is stationary sets. Okay, so you may be familiar with stationary subsets of a regular cardinal. There is a more general concept, namely a stationary subset of the set of all countable subsets of a given set. So we start out with the following definition, that a set C contained in, so we fix your favorite set capital X So when I write x to the omega, so this thing here, this is the set of all countable subsets of x, and x itself should not be countable, it should be uncountable, otherwise the concept is not very interesting. Okay, so C, a subset of the set of all countable subsets of a given set X, is called club, and club stands for closed and unbounded. If there are various ways to state it, we can say if there is a function from which takes finite subsets of X. So this is the, or let's say the finite sequence of elements of X. This is what this symbol stands for, the finite sequence of elements of X. Every finite sequence of elements of X is mapped to an element of X. So there is such an F, so that C is simply all the things from that space, which is closed under F, right? So that F so what I write here, that means that whenever you take a finite sequence from little x and apply the function f to it, then you end up in little x again, right? So in that sense, C is just the collection of all things which are closed under the function little f. You may think of the function f, for instance, or you may think of, we may, if we have capital X, we may think of f as a Skolem function, or rather we may think of x together with the function f as a model in the sense of model theory. And then the club just consists of all the countable substructures of that model, right? So if you look at this object, so C then is the set of all substructures of the model. Okay, so this is how you may want to think of a club. Here we are only interested in countable subsets of a given capital X, of a fixed capital X. There is a more general concept of a club and then of stationary sets, but this turns out this is not relevant for us. So I will focus on this particular situation. Okay.
I'm sorry. What's the mark on the upper right side of the F in the line of C equals 2?
C equals. I'm sorry. Could you say it again?
Okay. Okay. And what is the mark on the upper right side of the F in the line of the C equals 2? I just don't know what it is.
C equals 2.
Yes.
Where is the 2 here?
Image of F.
You mean this thing?
Yes, I mean this thing. What's the mark on F?
So what is the? Yeah. Okay. So okay. So the notation I'm using here. So F is this function which takes countable. And I'm sorry. F is this function which takes finite sequences of X and maps every such element to an element of X, right?
Yes.
So F. This is just the pointwise image. So this is the set of all f of u, where u is a finite sequence from x, right?
Okay.
So you just let u range over the finite sequences of little x, and then you look at all the images under f of these objects. You collect them together. And you require that all these things are again contained inside little x. So in that sense, little x is closed under under the function f. Okay?
Okay, thank you.
Sure, yeah, great. Right, so in general, the notation, you know, if you have any function from A to B, and let's say little a is a subset of A, I always write f of A with these two things as the collection of all f of u, where u is in A. Some people write it as with square brackets, and I use this notation. Okay? Okay, so that's what a club is. Maybe I have a little bit of space here to add something. This is just a comment, so let me write it into this box here. So instead of looking at, this is kind of an algebra, x together with a function f. You may also look at other models. You can look at x together. Let's say maybe you have a bunch of relations R on x, right? So maybe x is a, I don't know, transitive set, and maybe there is the epsilon relation on x. Maybe you have some other relations which you're interested in. You can pick for any such structure. You can pick Skolem functions and then let them act as a function little f. So you may also define a club as something if you have these kinds of things in mind. So you could say a club is a collection of countable subsets of your given x, so that you have a model and the club just contains of substructures of that given model. So this is how you should think, or how I think of a club. Okay? Okay, so now once we swallowed what a club is, we may very easily define what a stationary set is. So we say that a set S subset of the same space, S, a subset of the same space, is called stationary, and this is really a key concept, not only for our talks, but also for set theory in total. If S intersects C is non-empty for all clubs, for all C which are a club. Okay, if you think of the characterization of clubs which we just discussed, what does that mean? So that means that a set consisting of countable subset of your given fixed capital S is stationary if for every model with underlying universe X, and you have to add that the model has a at most countable signature, if for any such model there is a substructure of that model, a countable substructure of that model which exists in S. So why don't I write it down, right? So hence S is stationary if for all models X, so here you might use a function f as we had it in the definition before, or for all, you may consider more generalized models X, where you have some relations, or maybe some of the R's are relations, maybe some of the R's are actual functions, but this is at most countably many. So when I write R vector, I just mean it's a sequence of either relations or functions or both. Or for all models, there is some X in S, so that X is now I'm using this notation, X is a substructure. Oh, I'm sorry. now I'm confusing two different x's. So there is a little x in capital X, so that little x is a substructure of the given model. Okay. So stationary sets are sets so that for every model you have a substructure, a countable substructure in them. Okay. So let's get just familiar with this concept by proving the first lemma. So the first important lemma you can prove about stationary sets is by Fudan. So this is Fudan's lemma for this context. So let X, we fix a capital X, and as always, we think of capital X as being uncountable. So let S be stationary. And let's suppose you have a regressive function on S. The lemma of Fudan for subsets of a given regular kappa is a bit more familiar, but there is also a Fudan in this context, and we are going to prove it now. So let S be a stationary set in the sense we defined it, and let F be regressive in the following sense. So so F is a function which takes elements of S and maps them somewhere. So V is the letter for the universe of all sets. But what I want is that F of X is always an element of X for all X in capital S. Okay, so in this sense that it's regressive, then there is a stationary subset of S so that F restricted to T is actually constant. Okay, let me give a proof of this. Okay. Proof. Okay, so otherwise, these letters stand for otherwise. So let's suppose this is false. Okay. Otherwise, for all let's say A in X, the set of all X which are from S, so that F of X is equal to A. Otherwise, all these things are non-stationary. And we should introduce a name for this thing. Let's say this is S sub A, right? So you are guessing you want F to be constant on a stationary subset. So you fix the value little a from capital X, and you look at all the little x's from S so that F of X has value A. You would like to have one of them being stationary. So let's suppose they are all non-stationary. That means for all of them, there is a club which does not meet them, right? So there is a club which has empty intersection with, so for each little a, there is a club which has empty intersection with this corresponding set. Okay, so say you have a C sub A, which is the set of all X from our space, so that, so this is supposed to become a club. So the club is given to you by a function little f, as on the slide before. So the club is given as all the closure point under some function f sub A. Right, and I want that this is a club witnessing that the set S sub A is non-stationary. Okay. Okay, what we do now is we simply amalgamate all these functions basically, right? So we say, we define f of A. So A is a finite sequence from capital X. I'm sorry, I misspoke. So little a is an element of X, but we may let U be a finite sequence of elements of X, right? So I just define this one function f as, A followed by U is also another finite sequence of elements of capital X. So I can just say this is f sub A of U for U being a finite sequence of elements of X. So this is a new function. And this gives me another club, right? So let C be the club given by that. So f of, okay. Okay, so let's see what happens. If you take if you have an A which is actually in X and this is in C, right? Then it happens that X is an actual element of C sub A, right? So if little x is closed under the function f, but if A is also in little x, then it means that that little x is also closed under the function f sub A, right?
Excuse me.
Yes,
I think
of course.
you used F 2 times, right?
I'm sorry?
F was your regressive function and you define F again, or this is some G?
Oh, I'm sorry. Oh, I'm sorry. Yes, thank you very much. Too bad. Thank you very much. Okay, let's. I use the letter F for two different things. Thank you very much. Now we are okay, right? So F star is the kind of amalgamation of all the F sub A's. Yes, yes, they don't have anything to do with each other in some sense. Yes, okay. And now what we do is we pick. So C is also a club, right? So we may pick a little x which comes from S and also from C. Okay. And then we let, okay, so, f of little x is defined because x is in S. So let's call it little a. So this is an element of x by hypothesis. Okay. And then we have that x is an element of, right? I mean, little x is an element of big C, and A is an X. So by the line above, we have that X is also in C sub A. Okay, but what does that mean? So this contradicts the choice of C sub A, right? Because I mean, what's written here says that X is an element of S sub A. And here we have that X is an element of C sub A. So this gives a contradiction to the choice of C sub A. Okay, so the whole thing doesn't work. Okay, So this was the proof of Fodor's lemma. Okay, so this is an important statement, which with an easy proof. And it will play a little bit of a role later on. Okay. If there is any question, please feel free to interrupt. So there is a special case of clubs and stationary sets. So the special case is, this capital X is always our underlying set, and I said that it should be uncountable. The most canonical uncountable set maybe is is omega 1 or LF1, right? So, and it's very easy to observe that if S is a subset of, our given space in this particular case is this thing, or the countable subsets of omega 1, the most famous countable subsets of omega 1 are countable ordinals, right? And we can actually restrict capital S to the countable ordinals, and then we are still stationary if S was stationary. So if this is stationary, then so is the set of all psi in S, so that psi is an actual ordinal. Let me just write psi is an element of omega 1. And this is very easy. The proof is simply, I will more or less leave this as an exercise, but it's very, very easy. So if C is a club, then so is, you may just restrict to ordinals in C. Because if you reflect on it, I mean, there is a club in our given space which just consists of ordinals, right? Or the ordinals below omega 1 is a club. So you can always, it's very easy to cook up a model with underlying universe omega 1, so that every substructure, so that the universe of a substructure of it which is countable must be a countable ordinal. Okay, so you have this thing, and you get this observation. Okay, so a typical, what this says is a typical club in that space, omega 1 to omega, is actually a set of countable ordinals, and also a typical stationary subset of our given, of this particular given space is a set of countable ordinals. Okay. Now for this special case, there is an important theorem. I mentioned that there is also the concept of stationary subsets of a given of a general uncountable regular cardinal kappa, but I don't think we will need it, so I didn't want to talk about it. Let me erase this proof and try to put a theorem and a proof of it on that page, which will also be very relevant for us in the future. It's an important statement. So this is about splitting stationary sets. And we will actually use the statement, but we will also use the proof of that later on. So we will use a slight generalization of that in what is to come. Okay, so there is a theorem of Solovay, which says that if S is your favorite stationary subset of omega 1, as we said, a stationary subset of that space omega 1 to omega is without loss of generality. It just consists of countable ordinals, so we may write it as a subset of omega 1. we may split this thing into omega 1 many stationary sets, which have a pairwise empty intersection. So we may write S as the union of SIs, and I put a dot over this union symbol to indicate that this is a disjoint union. So any two SI has anti-intersection with Sj for I different from J, okay? And all Si are stationary. Okay, so let me sketch the proof of that, which is also fundamental. Proof sketch. So what you do is, it's basically not very difficult. We have omega 1, and if you have any, let's say, limit ordinal, so we may assume without loss of generality that capital S consists only of limit ordinals, because S intersect the limit ordinals is also a stationary set. Okay, so if you have a limit ordinal psi, you may pick a sequence of alpha n psi which converges to psi. Okay, so let me just write, so the a n psi's, they converge to psi. Right, so for every psi which is a limit ordinal below omega 1, you pick a countable sequence of alpha n's, and I call them alpha n psi's, which have supremum psi. Okay. Now the claim is that there is a natural number n so that for every alpha less than omega 1, if you look at the psi's in S, so that alpha in psi is at least alpha, that this is stationary. It's always stationary, right? So there is an index n, so that for any bound alpha less than omega 1, if you just look at the elements of capital S, so that the alpha in psi is above alpha, that this is always stationary. And the proof of that claim is easy. You just assume that that's not the case. You know, you just negate. So otherwise, for every n, there is a bound alpha n, right? So that this is not stationary for alpha equal alpha n. So what does that mean? That means there is a club Cn, so that Cn intersect the set of all xi's in S, so that alpha n xi is above alpha n, that this is empty, right? Okay. Now, we did not prove, because I cannot prove everything, the intersection of two clubs is always a club. So if you think in terms of models, this is very easy to see. If you have two models with the same underlying universe, you can kind of amalgamate them, right? You just take the structure on these two models, or the relations or the functions, and you construct you build a model which has both of these relations, right? And then a substructure of this new model is a substructure of the one model as well as a substructure of the other model. So this is a very easy proof of the fact that the intersection of two clubs is again a club. And the same works for countably many clubs, right? If you have countably many models, you can just amalgamate them to one model. So there is one model, so that if you have a substructure of this one model, it's a substructure of each of the countably many models, right? So if you amalgamate, we are always talking about models with at most countable signature. If if you have countably many models which have at most countable signature, then the amalgamated model also have at most countable signature. So the intersection of countably many clubs is a club, and therefore the intersection of all the CNs, this is a club, and therefore we may pick xi, which is not only in this intersection of the clubs, but S is a stationary set, right? Okay. And we can also pick psi bigger than the supremum of all the alpha n's. And then we get a problem, right? Then all the, so what does all that mean, right? So that part, so for one thing, I mean, alpha n xi is defined, but alpha n xi, because you are in Cn, alpha n xi must be smaller than the supremum of the alpha n's, and this is true for every n. So let's write an m here. Right, but we pick psi to be bigger than the supremum. So you have that this guy is always strictly, you know, that there is this one bound below psi, so that all these guys are smaller than this bound. So in other words, the alpha n xi's, they cannot be cofinal in xi, but we pick the alpha n xi's to be cofinal in xi. So we pick them to be souping up to xi. Okay, so this is a contradiction. So that proves this claim. And now let me.
Okay,
yes, of course.
The theorem you're stating is stating on omega 1, which is the successor
Yes.
cardinal.
Yes.
According to Kuhn's book, this is
Yes.
attributed to Woolen theorem. I think Soloway did that for
Oh, is that
generalize
true?
that to weakly inaccessible. Well,
Oh, I see.
more precisely, in Kuhn's book, the theorem stated that's for kappa. It didn't state it for stationary,
sure.
but for stationary, it's very easy the same way. You just intersect with the S.
You just intersect? Sorry?
I mean, in Kuhn's book, the theorem
Yes.
stated is for kappa, splitting
Yes.
kappa.
Yes, yeah, I mentioned.
For kappa as a successor.
Yes, okay, yes.
So I
Yes.
think that this, I mean, pretty much the same argument for
Yes, of course. It's the same
for
argument.
stationary.
Yes.
So what
yes,
I'm saying is more precisely, this should be a credit to Woolen. Soloway generalized that to arbitrary regular cardinal. In particular,
yes, I see.
inaccessible.
So I actually, I apologize. I wasn't aware of this historical thing. Yeah, I thought this is also okay.
But actually, the proof you were presenting here, I think that's a Soloway's proof, slightly different from a Woolen's proof, but the same idea though.
Yes, yeah. Okay, good. Okay. So this is sort of Soloway's proof of an older result. Okay. But anyway, we are now just proving it for this one case that S is a stationary subset of omega 1, and as was just said, this generalizes to other regular cardinals. Okay, so where are we? We verified this claim, right? So there is an n, so that above every bound below omega 1, if you restrict to the xi's and S so that alpha n xi is above alpha, this is always still stationary, right? This is a subset of S, and this is always stationary. And actually, there is more we can say immediately. Namely, if you have such an n, so that for all such alphas below omega 1, this is stationary. If you look at the function which maps xi to alpha n xi, this is regressive, right? If you fix this n and you map xi to alpha n xi, this goes down. So this is a regressive function. So by the proof of, or by Fodor's lemma, there is an actual stationary subset then, so that you are constant. So we can actually improve the claim. And let me erase this upper part here, and then I can finish the proof up here. Okay, right. So we can immediately improve the claim. So this is claim plus. So well, let me write it down like fix n. I don't know why this always happens. Fix n as in the claim. Then we may improve the claim to say that for all alpha less than omega 1, there is a beta above alpha, so that the set of psi in S, you know, this thing which is in the claim is stationary, but now we are pressing down on the alpha n psi's, and on the stationary subset this is constant, so we get one beta as a stable value, so that the psi's in S, so that alpha n psi equal to beta, that this is stationary. Right, this is an immediate consequence of Fodor's lemma from the first claim. Okay, and now we may just construct a sequence of SI's together with beta i's, and this I is less than omega 1, right? So what we do is we construct the beta i's as strictly increasing. Okay. So if the sequence of SI's and beta i's is constructed up to some point j, if Si, beta I less than j is constructed, right? You look at alpha being the soup of the beta i's I less than j. And let's add a +1 here in order to make sure that this gets strictly increasing. Okay, so to this alpha, you apply the claim plus. So you find a beta which sits above alpha, so that this set which I wrote down is stationary. And you call the beta from claim plus beta j. Beta j is the beta as in claim plus, and Sj is the stationary set from there. And then everything works, right? Because then these SI's which you constructed, they are all pairwise disjoint, because if you are in two different SI's, the corresponding alpha n psi's have different values, namely the respective beta i's, and they are strictly increasing. Okay, so this is Solovey's result. So I'm sorry that this screen got a bit messy, but I hope in the future I will do it in a more clean way. Okay. Okay. So I have another half an hour until the break. So this was the stationary sets. So this, for this moment, ends the discussion of stationary sets. So let me say a few brief words about forcing in general. So this is our next topic. But here I have to be really very brief. As I said, I am kind of presupposing knowledge of forcing for the sequence, for the series of my talks. So as I already mentioned, I will use the letter capital V for the universe of all sets. So what does forcing do for you? So forcing is the following method. You take a partial order P from the universe of all sets. P is a partial order. If you want to be a little bit more precise, then you make the actual order visible. So we often just confuse capital P with P together with the actual order on P. Okay, so so there is a key concept of a dense set. So D subset of P is dense if for all P in P there is a Q in D, so that Q is stronger than P. So by this symbol, so you have a partial order and it comes with this less than or equal relation, right? And we read Q smaller than P as Q is stronger. And usually when you define a concrete partial order, it's clear, it's often clear how the stronger relation should look like. Sometimes it's very important how exactly you define it. But anyway, this is the symbolism which is usually used. And then we say that a G, a subset of P, is V generic if and only if G intersect D is non-empty for all D subsets of P. Well, now I will add D in V dense. And it turns out that for the interesting partial orders, there are no generics inside V. So you have to step outside of V in order to see a generic. Now, if V is the universe of all sets, that means that for the interesting forcings, there aren't any generics really. But usually it's the best way to treat with this whole situation is that you pretend that when you talk about forcing, you force over V and you pretend there are objects outside of V. You can make this a bit more correct or formally correct if instead of V, you talk about, for instance, countable models of set theory or a countable substructure of a rank initial segment of V, and then there are actual generics. Okay, so this is how forcing works, and so the forcing, if you have a G which is V generic for a given poset, you make sense of the generic extension of V by G. This is the notation for it, by saying that this is the collection of all interpretation of names. So that here means that tau is a P name. Okay. So what is a P name? So a P name is, this is recursively defined. So this is a relation, elements of the forcing P, comma, a name. So a new name is just a collection of pairs, elements of the partial order together with names. So this is done recursively, and then the interpretation is the obvious thing. So the generic extension is the interpretation of all the names you find in the ground model. And there is an important thing named the forcing theorem. It has two parts. One part of the forcing theorem says that if in the generic extension, it's true that a certain statement holds true phi of tau g, comma, blah, blah, blah. So you have finitely many parameters. Then there is a P in the generic filter, so that P forces phi of tau, blah, blah, blah. So I did not define the forcing relation. You may think of saying that P forces phi as saying that whenever you pick a generic which contains P, then in the generic extension phi is true, pretending that every element of the partial order has a generic which contains it. Then that's a characterization, but this is something which the ground model V cannot see. It does not have access to generics in general, unless the forcing has atoms. Okay, so it turns out that, okay, now let's pretend there are always generics. Then it turns out that the ground model V can actually see this relation. And this is the key thing you prove when you develop the theory of forcing, that the relation P forces phi can be seen from the ground model. It can be defined in a syntactic way over the ground model V, even though you have it to mean that for every generic G which has P in it, phi is true in the extension. Okay, so this is something which apparently you cannot verify in the ground model, but in the end you can. Okay, so one key thing is the first part of the forcing theorem, that if something is true in the forcing extension, then there is an element of the generic which actually forces it. And the other thing is kind of the converse. If P forces phi of tau, then this is almost by definition, or this is by definition if you phrase it that way, then in the generic extension, this statement holds true for all. Let me just write for all G which are supposed to be V generic, but G has to contain P. Okay. So I was saying that I'm presupposing forcing. So this was my plan, was that's it what I want to say about forcing in general. I hope that's okay. Okay. So there is a very nice, the name of Fudan was mentioned in on two different occasions so far. So there is, if you want to see forcing, so there is Fudan's textbook. This covers forcing in a very nice way. And it also covers parts of what we are gonna do today. So I now want to turn to our next topic, which is forcing axioms. And I want to start introducing Martin's axiom. So this is what forcing axioms, this is what we are going to do for the rest of today. For now, until the break, we'll start introducing Martin's axiom. And then after the break, we start introducing the stronger forcing axioms. So in order to arrive at Martin's axiom, we have the definition that P, so P is a partial order. Always, we say that it has the CCC. And this is the countable chain condition. If there is no uncountable anti-chain, if P does not have an uncountable anti-chain. Okay, so what is an anti-chain? So A subset of P is an anti-chain if for all P and Q from A, if they are different, then they are incompatible. So that means there is no common extension PQ, there is no R in the forcing, so that R is stronger than P and R is stronger than Q. So in that sense, they are incompatible. Okay, so that's an anti-chain, and then a forcing has the CCC if every anti-chain is at most countable. Okay, so a classical example, I write C for it, so this is cone forcing. I should have given maybe this example before. Cone forcing. This is the set of all finite sequences of natural numbers. So let me write it down that way. Or you could also take the finite sequences of zeros and ones for that matter, for our purpose. So let's take the finite sequences of natural numbers ordered by reverse inclusion. So P is stronger in the cone forcing than Q if P just extends Q as a function. Okay, so this forcing actually has size L0, so it is countable. And then it's entirely trivial that there are no uncountable anti-chains, right? So this is actually the only, in some sense, countable forcing, and it's entirely trivial that it has the countable chain condition. But there are other versions of cone forcing, for instance, finite support products of cone forcing, which we might need at some point, I'm not sure yet, which also have the countable chain condition, and the proof then is more involved. Okay. So, so let me introduce Martin's axiom. So kappa here is your favorite cardinal, usually an infinite cardinal, but formally you could also even take it as a finite cardinal. So MA kappa, so this is Martin's axiom. For kappa. So this is the statement that if P has the countable chain condition, and D is a collection of dense sets of size at most kappa, a collection then there is a filter So, you know, we would like to say that there is a generic filter, which we cannot, because as I mentioned, in general, there are no generics in V for a given non-trivial forcing, but sometimes there could be kind of partial generics, and this is a way of spelling out that there is a partial generic. You don't want to consider all the dense sets whatsoever, but you limit the number of dense sets you want to meet by a given filter, and then you say, okay, and then I have a filter which does it. Then there is a filter G contained in P, so that G has non-empty intersection with any of the elements of D. Okay. So I presupposed what a filter is. A filter is just a collection of elements of the partial order, so that if something is in the filter, everything weaker is in the filter. And if two things are in the filter, they are compatible, and which is then mostly equivalent with saying that two things in the filter are compatible as being verified by something in the filter. Okay, so this is a filter, and the generic filter is something which meets all the dense sets whatsoever, which are defined, which are elements of the ground model. And in this case, what we do is we only consider a fixed collection of kappa many dense sets. And then we say that kind of in V we have a filter. Okay, so this is an internal axiom. This is kind of internal forcing. You're not stepping to a forcing extension. You're saying that fragments of what would exist in a forcing extension already exists in the ground wall. You don't have to force. The filter is already there. This is very important. Okay. So let me give some fairly. So we are still at the level of introduction and of things being kind of, in some sense, elementary. So let me give you some examples. So MA omega, this is simply true. Why is it true? This can be proven in ZFZ. Why is this? If you have a collection of countably many dense sets, right? What do you need in order to verify MA omega? So it doesn't even matter that the forcing has to have the CCC. It works for an arbitrary forcing. Okay. So if you have countably many dense sets, you can just construct a sequence of P sub n's so that P sub 0 is in your first dense set, P sub 1 is in the next dense set and is stronger than P sub 0. They are all dense, so there's no problem with such a construction. P sub 2 is in the next dense sets and it's stronger than P sub 1, and so on and so on. And then you take the filter as everything being weaker than one of the P sub n's which you have constructed. So this gives you a filter, and by construction it meets all the dense sets, so there is no problem with that. So this proof actually also shows that if you have a countable model and a forcing in the countable model, then there is a generic filter over that model, which is generic for that model. Okay, so MA omega is always true. On the other hand, MA, there is a limit on the size of kappa which you can allow. So MA sub aleph 0 is simply false. And maybe we should quickly do that proof, even though it's very simple. Namely, that uses cone forcing. Okay, so we said that cone forcing trivially has the countable chain condition. So what we can do is as follows. So, suppose MA sub 2 to the aleph 0 were true. Okay, so let's see. So let x I less than 2 to the aleph 0 enumerate all the functions, all the elements of the Cantor space. That's exactly the same size as the continuum, or as 2 to the aleph 0. So all the infinite sequences of natural numbers. Okay, and now corresponding to an xi or to an index I can define a dense set d sub I. That's the set of all P in the cone forcing, so that P disagrees somewhere with xi, so that there is an n. Remember that the elements, I'm sorry, I should not write P, I should write C here. The elements of the cone forcing are finite sequences of natural numbers. So what I want to say is there is an n in the domain of P, so that P of n is different from xi of n. Okay. So this is easily be seen to be a dense set. This is more or less trivial. If you fix x sub I and you're given any condition in the cone forcing, you can easily extend it to a stronger condition by enlarging it if necessary, so that at some n, the value is different from xi of n. You know xi of n, xi is fixed, so you can just let the value at n be something different. Okay, so all these things are dense. So the collection of the di's I less than 2 to the aleph 0, this is a collection of dense sets. Right, but there can be no generic which meets them all, right? So if G intersect DI is non-empty for all I less than 2 to the LF0, by throwing in a few countably many more dense sets, you can make sure that the union of G, you know, if you kind of knit them all together, that's a function from omega to omega. So this would be just one of the xi's, right? We are not stepping outside of V, we are staying inside of V. We are assuming that MA 2 to the Aleph 0 is true. So the union of the G's is equal to xi for some I. Right, but this is an obvious nonsense, right? Because so for this particular I here, G intersect DI is non-empty, which means that at some place a P from G has to be different from, so there is a P from G, so that and an N, so that P of N is not equal to Xi of N, which simply means that the union of the G of G at N is not equal to Xi of N, but this is just Xi of N. So this is a plain contradiction. Okay, so you cannot meet too many dense sets. So in other words, the only thing which you can hope for to be consistent is Martin's axiom kappa, where kappa is less than the size of the continuum. Okay, so we can state this in a kind of more positive way. We could say that if MA kappa holds true, then kappa is less than the size of the continuum. Okay, and it turns out that this is MA kappa for kappa less than the size of the continuum is consistent. Okay, let me just finish the first part before we make a break by saying what I'm planning to do after the break. So after the break, we will use almost disjoint coding. AD is equal almost disjoint. You know, I have to start sketching some proofs, so we cannot do it really fully, but I will do it more or less. Almost disjoint coding, as it's called, to show that Martin's axiom sub, we saw that Martin's axiom sub omega is just a statement of Z of Z. Martin's axiom sub omega 1 implies that the continuum is at least Aleph 2, as we realized. So this implies that actually 2 to the Aleph 0 is equal to 2 to the Aleph 1. And of course, this statement again has a generalization. This is a statement which is known as Suslin's hypothesis. Okay, I have a couple of more minutes. So in order to get ready to prove that, let me just end with something very simple, namely the following claim, that there is a sequence, there is always a sequence sub xi less than omega 1 of subsets of omega actually, let's work with of subsets of omega, so such that the sequence is pairwise almost disjoint. So what does that mean? That means that such that for all xi and eta less than omega 1, xi different from eta, a xi intersect a eta is at most is finite. And in fact, instead of omega 1, I could simply write 2 to the aleph 0 here. But we don't need that for the argument, actually. So how do you get such a thing? This is very simple. So proof. You could either do a recursive construction, but you can also just write it down. So look at what's sometimes called the binary tree. So you look at all the finite sequences of zeros and ones, and you order it by end extension. Okay, so this is some kind of tree, right? At the bottom node, you have the empty sequence. Then you have the two sequences of length 1, one putting a 0 in there and one putting a 1 there. And then you have all the sequences of length 2, you have all the sequences of length 3, and so on. Okay, but you can also, you know, the idea is simply that any two branches through that, any two infinite branches through the tree correspond to subsets of this thing, but this is this has the same size as omega, right? So let E be a bijection right? So for all, so what are we going to do? You simply let B sub psi less than omega 1, and I could, instead of omega 1, simply write 2 to the aleph 0 here. Let this be a sequence of pairwise different branches through the tree, right? I construe this object as a tree, so a branch is a maximal subset so that any two elements are compatible in the sense of functions, right? So I trivially have continuum many pairwise different branches through this tree, but then they are, because they're simply different, they are they give rise to almost disjoint subsets of omega, right? So let A sub psi be simply be the collection of E of B sub psi restricted to n, where n is a natural number. So in other words, I just associate a finite initial segment of such a branch with its value under the function E. And if I take all these things, then these guys are now all pairwise disjoint, right? So the E psi do it. Okay. Okay, so this is a necessary ingredient for what we're going to sketch after the break. So we discuss Martin's axiom, and then we will move on towards proper forcing and the formulation of the proper forcing axiom. So I would suggest to make a little break now.
Yes, thank you, Professor Schindler. So
thank you very much.
So we should have I think half an hour break.
Yeah, that's nice. Okay.
Okay.
Okay. And if you have any, if you feel like you should ask a question, we could also start out after the break with answers to questions or something. We could discuss what was done so far. Okay. Okay. We'll see you soon.
Start the second half of today's lectures.
Okay. Thank you very much. First, I would like to ask, is there any question about anything we did so far, or should I go back to something? Or should we just continue? Let me mention maybe, I told you that I will mention some references. So there is a paper by Tom Yek which is called stationary sets. And that's in the handbook of set theory. And this covers much more than, it's this book. It covers much more than anything we did about stationary sets so far. And I already mentioned that Fudan's book has a very nice account of forcing. So maybe I just write it down again. Set theory. So these two are the references for today. Not quite, because we will, Yek's article also has a section on proper forcing, but I don't think it has a section on the proper forcing axiom. But anyway, I mean, in some sense, these two papers serve as a good references for what we are going to do today. Okay, so I would still like to do things which are in textbooks. So as I mentioned before the break, what we now want to show is the following theorem. And again, my historical knowledge is very weak, so I actually don't know who proved it. I don't know. Martin's axiom omega-1 implies Suslin's hypothesis. Using almost disjoint coding, so maybe was it Solovay who proved it? I'm not sure. Okay, so let's do the proof. Okay, because it illustrates a lot of things which we did so far, and also it is kind of important for us to know when we study higher forcing axioms. The higher forcing axioms which we are going to introduce all imply Martin's axiom at Aleph-1. So everything we can prove from Martin's axiom at Aleph-1 also follows from the higher forcing axiom. So for instance, this kind of coding we are doing now. Okay, so before the break, what we said that it's always possible to fix a sequence of pairwise almost disjoint subsets of omega. So we fix that. So we let A sub psi less than omega-1 be a sequence of pairwise almost disjoint. So this is almost disjoint subsets of omega. And we saw before the break how to get such a thing. They cannot be, because it's Aleph-1 many, they cannot be completely disjoint, but they are almost disjoint in the sense that the intersection of any two of them, of any two different of them, is finite, right? So now we want to kind of do a coding modulo this one given fixed sequence. So what we want to do is we want to code a subset of omega-1 by a real or by a subset of omega in a way that the coding is injective. So in the end, we want to get an injection from the power set of omega-1 into the power set of omega. And that's a forcing which does the job for us, okay? So we fix for a while. So we let X be a subset of omega-1 and think of the goal as coding it in some way by a subset of omega. So this is done by a forcing which meets the generic, or the filter, the partially generic filter has to meet enough dense sets in order to let things work out. Okay, so we define the following corresponding forcing. So we let a condition be in the forcing if and only if P is a pair, F and let's say little x, so that F is a function from a natural number into 2. Remember that for us set theorists, a natural number n is just the set of natural numbers 0 up to n minus 1, right? Sorry, was there a question or no? And X is simply a finite subset, you know, this is this capital X, finite. Okay, so this is the capital X corresponds sort of to indices of elements of the sequence of the stationary sets. Okay, now the forcing itself is very easy, but the forcing relation is a bit more difficult. So you say that f prime comma x prime is stronger than f comma x in that forcing, if and only if, well, the stronger function just extends the easier function. You enlarge the set in the second component. But the key thing is that if you have an M, which is in the domain of the function f prime, but not yet, right? I mean, you enlarge the function f to a function f prime, so you have new things in the domain. And whenever you are in this domain, you want to say for everything there, so that f prime of M is 1, then this is entirely disjoint from xi for every xi in X. So this X is the X up here, right? So basically what's going on is that if you have a condition f comma x, once an index xi is in little x, you promise that if you enlarge f, the function f, then you're doing it in a way that the characteristic function, that this bigger f prime is the characteristic function of a set, which is going to be almost disjoint from xi, right? So right. So for instance, okay. So the set of all pairs f comma x, so that n is in the domain of f. So for any given natural number n, this is certainly a dense set, and these are omega many. So if we meet all of them, we will get a generic filter so that the first components of the elements of the generic filter, they line up to give a function from omega to 2, right? And this function from omega to 2, you construe as the characteristic function of a subset of omega. And then the way how the extension of the forcing is designed makes sure that if a xi is in one of the little x's, then this subset of omega is almost disjoint from a sub xi. Okay, so let me see. I will go to a next page. Okay. Where is it? No, it's not good. No. Why can I now not? What's going on? Sorry, it says that I cannot. Done. Alle Zeichnungen löschen. Okay, now here we go. Okay, so maybe I should remind you. So f prime, xi prime is stronger than f xi if you extend the functions, you extend the sets. So this is always a subset of capital X, which in turn is a subset of omega 1, which is fixed for the forcing. Okay. And you have that the m's in the new domain in the new part of the domain, so that f prime of m is 1 intersect xi is empty for all xi in little x. Okay, so we said that the set of f comma x, so that n is, so that n is an element of the domain of f, that this is always dense for all n. And also we have that the set of xi in big X, so that xi is in, I'm sorry, I'm writing this in the wrong way. The set of all fx, so that xi is in little x, is dense for all xi in capital X. Okay, so this immediately gives that that the generic gives rise to a function. Maybe I should call it capital F from omega to omega. Gives rise means that this capital omega is the union of all the little f's, which are first components of the generic. So this is a function from omega to omega because all these first kinds of sets are dense. Okay, and it will have, because of the genericity of the second thing, it will have the property such that for all xi element x, the set of all n in omega, so that f of n is equal to 1 intersect a xi is finite. Right? You cannot say that it's empty because maybe there is a condition in the generic where the xi is not yet contained in the little x, but eventually you can put xi into the second component of the condition, and from that point onward you will be disjoint. So that's true. Okay. And on the other hand, by the way, how things work is that if xi is not an x, then the set of things f sub x, so that, well, now we have to say, so that there is an m bigger than or equal to n, so that m is in a sub xi, and f of m is equal to 1, so that is also dense for all natural numbers n, and for all xi, this is already written here. Okay, so if you have xi not in capital X, then it's never forbidden to extend a condition in a way that there is an m bigger than your given bound, so that m is an a sub xi, and actually f of m is equal to 1. So you have the opposite of what's required here, up here. Okay, I mean, here you are only talking about xi's which are in small x, and small x is always a subset of capital X. So you're never gonna have any kinds of restrictions like that for elements xi which are outside of capital X. And it's the case that if xi is outside of capital X, it's never forbidden that that f of m is equal to 1 while m is an element of a sub xi. So this is also dense. So all these things are dense, and that means that if you are generic, right? So if a generic is at least partially generic and it meets all these sets which are written up here, so these are so far only L(1) many dense sets, then you have the properties which are listed here. Okay, and if now you have on top of it, if you have a generic which meets all these dense sets, these are also again only L(1) many, then you will have the property that for all xi which are not in capital X, the set of all n in omega, so that f of n is equal to 1, yet n is an element of xi, is infinite. Okay. It takes a little bit of an argument. We didn't really prove it, but it's easy to see. We didn't prove the density of that set, but that follows from the fact that these sets are pairwise almost disjoint. Okay, so you will have this key property. So you will have the property. Okay, so you will have the property in sum if G meets all of the following dense sets of the following dense sets, right? It's what we had, the set of f sub fx, so that n is an element of the domain of f for a natural number, the set of fx, so that xi is in little x, for xi is in capital X, and the set of all fx, so that there is an m which is at least as big as n, so that m is in a sub xi, yet f of m is equal to 1 for an n less than omega, and a xi which is not in X. So these are L(1) many dense sets. So if you meet all of them, then the generic gives rise to some function f from omega to omega, such that if, I can write if A is the subset of omega 1 such that f is the characteristic function, of A, right? So capital F of n is equal to 1 if and only if n is an A, then A intersect xi is finite if and only if xi is an X. And that's true for all xi less than omega 1. So this is the sense in which little a codes capital X modulo the fixed sequence A sub xi of pairwise almost disjoint sets. Okay, so little a codes capital X. So this is a subset of omega 1. This is a subset of, this is a subset of omega, this little a, and the capital X is a subset of omega 1, codes X modulo the sequence of the A xi's for xi less than omega 1 in that sense. Okay. Okay, and once you have that, it's clear that now, okay, now if we assume Martin's axiom L(1), this means that for every capital X, we have a little a which has this property that little a codes capital X in that way for our fixed sequence of pairwise almost disjoint sets A sub xi. So for every capital X, there is a little a like that under Martin's axiom Aleph1. And then we may just pick for each capital X some such a, right? So if, oops, wait. So if we have Martin's axiom Aleph1, this means that for every x less than omega, for every x subset of omega 1, there is an a subset of omega. We just argue that for every capital X there is an a, so that for all xi less than omega 1, xi is an x if and only if a intersect a xi is finite. This is a very robust way of coding capital X by little a. So the sequence of the xi's is our fixed sequence of pairwise almost disjoint subsets of omega. But then we may just define a function, right? Let's say, let's call it capital G. It's a function from the power set of omega 1 to the power set of omega. You just map x to some, using the axiom of choice, you map it to some a. So the x comes from here, the a comes from here, some a with this property. And then, of course, this is an injective function, right? Because from little a, you can read off capital A in this fashion, and therefore the function is injective. And when you have an injective function from the power set of omega 1 into the power set of omega, then that means that 2 to the LF1 is at most 2 to the LF0. But of course, that means that 2 to the LF1 is equal to 2 to the LF0, and that's what we were trying to prove. Okay. So this was the proof that under Martin's axiom omega 1, you have Suslin's hypothesis that 2 to the LF1 is equal to 2 to the LF0, and the proof gives a little bit of more information. It actually shows that under Martin's axiom LF1, every subset of omega 1 is modular a fixed sequence of pairwise almost disjoint subsets of omega coded by a subset of omega or coded by a real. So the reals code the subsets of omega 1, which is a special feature of this forcing axiom. Okay. Okay, so where are we at this point? So we introduced, as far as the forcing axioms go, we introduced Martin's axiom at kappa. We said, just to recap, we said that MA omega is always true in ZFZ, and we said that MA 2 to the LF0 is false in ZFZ. Okay, which leaves the question, is MA kappa for kappa less than the continuum true? So for instance, if you have the continuum hypothesis, if 2 to the LF0 is equal to LF1, then kind of MA omega is true and MA omega 1 is false, and that's it, right? So this is in some sense not a very interesting situation. So what we just used was MA omega 1, which implies the negation of the continuum hypothesis, because we showed that 2 to the LF0 is equal to 2 to the LF1. right? This is what we showed under MA omega 1, and 2 to the Aleph 1 is at least 2 to the Aleph 2. So the continuum is at least Aleph 2 under Martin's axiom at omega 1, right? Okay. We didn't yet talk about whether these stronger forms of Martin's axiom sub kappa for kappa bigger than omega would be consistent. And it turns out that it is. So if you look, for instance, in Kunin's textbook, there is the last chapter which proves the consistency of MA kappa for every kappa less than the continuum, and the continuum being larger than Aleph 1. So one can show kappa bigger than Aleph 1 and what do I want to write? I'm sorry. One can show that the continuum being bigger than Aleph 1 and MA kappa for all kappa less than the continuum, so that this statement is consistent. So how do you show that it's consistent? There is an iteration of CCC forcings, which, for instance, forces that MA sub Aleph 1 is true and the continuum is size Aleph 2. But I don't want to talk about it because we want to go for even more powerful or stronger forcing axioms, and we will show the consistency of these stronger forcing axioms hopefully tomorrow using a large cardinal. Okay, so we will go ahead and discuss more powerful forcing axioms. You know, you can also show that Martin's axiom omega 1, for instance, does not decide the continuum. You can also have that the continuum is Aleph 3 and you have Martin's axiom sub Aleph 2. That's also consistent. It's kind of implicitly stated here in some sense. But the stronger forcing axioms have the peculiar implication that they actually decide the size of the continuum. And this is something kind of surprising. If you come from Martin's axiom, you would think it's very easy to make the continuum very large in the presence of Martin's axiom, but it turns out that if you strengthen the forcing axiom by relaxing the class of forcings which are involved, that then you actually get a decision on the size of the continuum. This is a very surprising thing if you see it first. And this is what we want to go now for. And I actually will prove tomorrow that this stronger forcing axiom, which we are going to introduce, actually decides the value of the continuum. This is something I want to show you. Okay. Okay, so the rest of today's talk so we actually still have 1 hour. So we will introduce proper forcing, semi-proper. These are technical concepts, and stationary set preserving forcings. And they all correspond to forcing axioms, which are called, surprisingly, the proper forcing axiom, the semi-proper forcing axiom, and Martin's maximum. And I want to state a formulation of Martin's axiom, which is less commonly known. Okay. So, and I can only repeat, if you have any questions, please feel free to interrupt me either by just writing something in the chat and ask, or by just asking. Okay, so let's turn to proper forcing, which turns out to be a generalization of CCC forcings. proper forcing can be fairly easily defined in terms of stationary sets as we introduced them at the beginning of today's lecture. So we can say that a forcing P is proper. So if I write a P like that, it's always a partial order, and we always think of it as something we want to force with. Okay, so P is proper if for all x, remember that we define stationary sets as something which is a subset of x to the omega, the countable subsets of x. If for all x, if an S is a subset of x to the omega, which is stationary, then S is still stationary in the generic extension. So now this is a symbol which so far I didn't use. So what does it stand for? So this means that whenever you pick a generic G, which is V generic for P, then in the generic extension V of G, you would have that S is still stationary. Now, why is this not a trivial fact? It's non-trivial because you can easily make it false. So not every forcing is proper. So for instance, the easiest example of a forcing which is not proper is a forcing which just collapses omega 1 to omega. So for instance, the collapse of omega 1 to omega. So this means that generically, by finite conditions, you add a surjection from omega onto the old omega 1. This forcing makes omega 1 countable in the generic extension, and you know, omega 1 itself is a stationary subset of omega 1, but omega 1 is a countable ordinal in the extension, so for sure it's not stationary in the generic extension by this collapse. So that's the easiest counterexample. We will see later that every proper forcing, I'm sorry, the other way around, that every CCC forcing is proper. Okay, so there are non-proper forcings, and therefore there are also non-CCC forcings. Okay, so this is an easy example. There is a more complicated example which is useful sometimes in set theory. So for instance, you can take a stationary and co-stationary subset of omega 1. So you take a subset of omega 1 which is stationary and the complement is also stationary. No problem with this kind of thing. We saw, I wanted to say Solovey's result, but I learned today that it's older than Solovey, that you can split every stationary subset of omega 1 into omega 1 many stationary sets. So in particular, you can split omega 1 into two disjoint stationary sets. So if you have a set so that also its complement is a stationary subset of omega 1, then there is a forcing which actually shoots a club through the set. Okay, so you make the complement, which used to be stationary, non-stationary because the club you add is non-stationary. So why don't I write it down? So there is another forcing. The first example. The second example is let S be a subset of omega 1, so that S is stationary and the complement of S is also stationary. Okay, there is a forcing which adds a C, a subset of S, a club, but every stationary subset of S remains stationary. So in particular, omega 1 of V is not collapsed. Not like in the first example, right? So it's a non-trivial example. So omega 1 is not collapsed. It's not becoming countable in the generic extension. And even in the stronger sense that stationary subsets of S remain stationary, but the complement of S, because you shoot a club through S, C is a witness to the fact that the complement of S is no longer stationary. So you killed the stationarity of a set in a sort of pretty mild way, you know, as mild as possible. Okay, but C witnesses, I don't know, can you still read it? I can't read it if I write down here. Okay, so this is a non-trivial example of a poset which is not only not proper, it also kills stationary subsets of omega 1, and the collection of posets which preserve stationary subsets of omega 1, this is the last item in this list up here, is a very important one in set theory. And it will lead to Martin's maximum. Okay, so we defined the concept of proper forcing. Let me discuss this a little bit more. There is another important definition related to proper forcing. So let X be a substructure of H theta. So this is the collection of all sets which are hereditarily of size less than theta. So this is some kind of a rank initial segment of the universe. I would like to write just V there instead of H theta, but in ZSZ you cannot prove that there are any proper substructures of V. So let's write H theta. So let X be a substructure of H theta. For the definition, we don't need anything about the size of X, but usually we only restrict attention to countable substructures. So let me just write it there, countable. And let's say we have a P. So we also fix a forcing a poset, a partial order P. And we have a condition in P which happens to be in the substructure. Okay. In this situation, you say that a condition Q, which is stronger in the poset P than P, is X generic. This concept is due to Schindler, and the concept of proper forcing is also due to Schindler. If for all, usually you talk about ordinals, but you can talk about arbitrary elements. So if for all names of objects in the generic extension, so I pick a name for an object in the extension which happens to exist in the countable substructure, and the name is supposed to be such that it's forced by the trivial condition of P. We always assume that there is a trivial condition of P. It's forced that this tau is an actual element of H theta. You know, names can denote any kinds of things. They can denote stuff outside of V. But there are canonical names for elements of V. These are these check names, right? So if you solve forcing, you know that every element of V has a canonical name, X check. But there are also complicated names for elements of V, right? It could be that something is a name for an element of V, but it's complicated, right? It's not immediately clear what it should denote. So it's one of these things. This is the situation here. So you have a potentially very complicated name, but for an object in the ground model, okay? So for all in this situation, we have that Q actually forces that tau is an element of X. So in other words, every name of an object of the ground model which happens to exist in the countable substructure is forced by Q to be an element of that countable substructure. Right? It's absolutely non-trivial, even if a name if a name is an element of the substructure and it's forced by the trivial condition to be an element of the ground model, maybe maybe the name is not forced to be an element of the substructure. So if you think of if you collapse everything, if you collapse omega 1 to omega, right, in this example we had before, call omega 1, right, the name for the generic gives canonical names for every element of omega 1 for every countable ordinal, right? So you have this name for the surjection from omega onto omega 1. So every countable ordinal has a canonical name by saying, well, it's the image under some natural number under this function, right? And there is no hope that for this collapse forcing of omega 1 to omega that there would ever be any X generics. And I should have apologized. There is no capital X here. This is a small x. Okay. Okay. So this is a non-trivial thing, and now it actually turns out that the following is true. But maybe I write it down on the next page because then I can do the argument on the next page. So this is an important concept in the theory of proper forcing, because we have the following lemma. The following are equivalent. So we fix the forcing, I don't write it down. So P is a fixed forcing. So P is proper. And the second thing is that for all, this stands for all countable substructures X of some H theta. So X is countable here. And theta is sufficiently big for all P in P and also in the substructure. There is an extension Q of P, which is actually X generic. Okay, so proper, by definition, as we gave it, a forcing is, when you define proper forcing, you talk about the fact that stationary sets of the ground model are preserved as being stationary sets. And this second statement now shows that there is a completely internal characterization of being proper. Of course, the first one is also internal because you don't really have to go to the generic extension to phrase it. Okay, but this is anyway, it is a reformulation, and in order to illustrate things, I at least want to give this argument. We are now leaving, as far as references go, we are now certainly no longer, it's no longer in Cunan's book, and it's also not in the article by Tom Yeck, which I gave you before. So for instance, the book by Tom Yeck, set theory. This has the proof which we are now going to give. Okay. But let me make some space here. Okay, so let's prove this as an illustration. So let's do one direction first. So what do we have to do? So we fix a stationary subset of something. So let's fix capital X and let's fix X S, where there's a stationary subset of this space here. Okay. We saw from these examples that it's non-trivial that stationary sets are actually preserved. And there are many more examples, more trivial examples, more involved examples. You could preserve stationary subsets of omega, but then there are other more complicated stationary sets which are not preserved. I didn't give these examples just because of time constraints. There are all kinds of things. So anyway, so we fix the stationary set, and we need to show that under hypothesis 2, this set remains stationary. So what we have is, we have to pass to a generic extension by P and show that this S still meets all the clubs in the extension, right? It meets all the clubs in the ground model, but in the extension, there are new clubs. Maybe they are so thin that S doesn't meet them. So in order to show that, it suffices to see that if we have a P which forces that C dot is a club, so C dot is a name, in here, let's say C dot is equal to the set of countable subsets of X, right? This is all forced by P, so that the club is given as the closure points under the function f, and this function f also has a name. So f dot is a name for a function whose closure points are the elements of the club C. Okay? Okay, suppose this is forced. So what we need to see, so this becomes a density argument, right? In order to show that S remains stationary, it suffices to see that whenever you have a condition P which forces that C dot is a club, there is an extension of P which forces that C dot intersect S is non-empty, right? Okay, and the trick is that you simply well, we know that the second hypothesis is true, so we may pick an X, which is a countable substructure of H theta, theta just big enough, so that all kinds of things of current interest are in X. So P, C, dot, F dot, the forcing, what have you, they are all in X. And also, the collection of such substructures with the properties so far, this is a club, okay? But capital S is a stationary set. So if you look at little x intersect capital X, because S is stationary, we can add to this that X intersect capital S is actually in S. Possible as S is stationary in V, right? This takes place, the whole argument takes place in V, right? And now what happens is, now let me become a little bit sketchy. So what we simply do is you pick an X generic. Okay. And you verify that Q is as desired, as you wanted, right? We said we do a density argument. We want to show that there is a condition which is stronger than P, which forces that C intersect S is non-empty. So the key claim is that Q forces C dot intersect S is non-empty. And in fact, what we want to show, or what we have, is that Q forces that X intersect X. So this is an element of the ground model. So it has a check name that this is an element of C. So this is the key claim. But this just follows from the fact that from the definition basically. From the definition of X genericity. You know, we simply have to see how do you show that Q forces what's written here, namely that X, little x intersect capital X is in C. You have to show that Q forces that this thing is closed under F dot. Okay, but for every element, if you take an element U, a finite sequence from X intersect capital X, if that's in X intersect capital X to the less than omega, then it's forced by Q, you know, then that F dot of U, that's a name for an element of the ground model, but that name is also an element of little x, and Q forces that this is actually in X intersect X, because Q is X generic, right? And this is how you prove that Q forces that X intersect X is an element of C. It's just the definition and the choice of everything. Okay, so this is this one direction. Okay. So let's go to the other direction. So we want to show, maybe I erase, maybe I stay on this page and I erase the part of the proof we did so far. Oh, oops. Here. There's probably a more efficient way to do it, but I don't know how. What's going on? Okay. Well, this somehow is extremely inefficient. Okay. So, okay. So we prove 1 implies 2, or we give a sketch of that direction. Okay. Suppose we have, what do we need to see, right? Okay, we want to show that, we want to show the statement 2, and it turns out, okay, I'm not doing the whole proof. We want to show that for every X substructure of H theta, this property holds true. It turns out that this is actually equivalent to saying that there is a club of substructures X of H theta, so that every P in the substructure can be extended to an X generic condition. Right, so what we want to see is we don't need to verify that that's true for every substructure. It suffices to verify that there is a club of such substructures. And if that's not true, then there is a stationary set where it's false. Okay? So otherwise, the set of all X countable substructure of H theta. So theta is fixed and sufficiently big, okay? Such that there is a P in little x and in the forcing, so that there is no Q, which is stronger than P and is X generic, that this is stationary. Because the things for which you can have generics, this is not, does not contain a club, and therefore the complement is stationary, and this is the complement. Okay. Okay, this is a nice stationary set to look at, and we know that by hypothesis the forcing preserves stationary sets, right? So the first step here is now that we proved in the very beginning of today's lecture the result of Fodor. Look, we have a stationary set. It consists of countable substructures of h theta. So this h theta is now our capital X, right? So we have a stationary set, and we have a regressive function. If you look at a little x in that set, you can map it to one of the conditions in that set for which there is no x generic, right? You look at the function which takes x and maps it to a pi without a stronger x generic. So this is a regressive function in that sense, and there is a stationary subset on which this function is consistent, right? So there is a stationary subset T subset of X such that there is one P such that there is one P so that for all X in T, P is in X, and there is no Q extending P so that Q is X generic. Good. This is by Fudan. Okay. But now what we do is we simply, so again, I have to be a little bit sketchy, but I'm just trying to give you an argument. And if you want, you can go back and look at Tom Yeck's book where the argument is given in detail. So what we now do is we pick a generic. Okay, so we have this one stationary set and this one condition, right? So we pick somewhere outside of V, you pick a G, V generic for P, such that this little p is an element of G. Okay, so we know that S is still stationary, or T is still stationary in V of G by hypothesis 1, right? We don't kill stationary sets. Okay, so what does that mean? That actually means that you can pick we may pick an accountable substructure X of, so we go to some larger theta, which I call capital omega, okay? So this is capital omega. Think of H sub omega as again being V if you are not precise, okay? So X is a countable substructure of the new H omega, so H omega adjoint the generic G, X countable, so that X intersect H theta is actually in S. This is possible because S remained stationary in the generic extension. Okay, and then you see that you get a contradiction. So what you have is that if tau, so right, X, little x intersect H theta is in, I'm sorry, I didn't want to write S, I wanted to write T here. So now we are, here we go. Okay, T is still stationary. Okay, so if tau is a name which happens to be in, well, you need to look at the trace this thing, right? So if tau is a name for a ground model element which is in little x intersect the ground model H theta, okay, then tau of G is actually an element of X intersect I'm sorry, I'm missing a hypothesis here, namely that it's forced by the trivial condition that tau is an element of H theta, then tau G is clearly an element of X intersect H theta, right? Because, well, this is what's going on if you look at things, okay? And this is just forced. This whole thing which I wrote down now, this whole statement is forced by a condition, by some Q, which without loss of generality is stronger than P, and that's it. Okay, so I'm basically not giving any details here. I just wanted to give you the flavor of the arguments, trying to convince you that it's true and trying to show you the importance of this concept of being proper, that it can be characterized in this fashion. Okay, why is it important for us? So we now formulated being proper in terms of the existence of X generics for countable substructures of H theta. So there is a concept which weakens this requirement. So we have a definition. Okay, so let again X be your countable substructure of some H theta, X countable. And again, you have a condition P in a forcing, so P is a fixed given forcing, which happens to be in the countable substructure. Then by way of definition, we say that a Q which is stronger than P is, so before we defined X generic, so that meant that whenever you have a name for a ground model element which happened to be in the substructure, then it's forced by Q that the interpretation of that name is an element of X. Okay, now we restrict attention to names for elements of the ground model which are actually names for countable ordinals. So this is a very special thing. Okay, so we say that Q is X semi-generic if for all names tau in V of P, which happen to be elements of X, so that the one of P forces that tau is an element of omega 1, so it's a name for a countable ordinal, we have that Q forces that tau, well, I could write that tau is an element of X, but you know, it's already forced by P, or it's already forced by the trivial condition that tau is actually an element of omega 1. So if you are forced to be an element of X and the element of omega 1, so that, right, so that's equivalent to saying that tau is an element of X intersect omega 1, check. Now, X is a countable substructure of H theta. X intersect omega 1 is an ordinal, right? So so for one thing, little x has all the finite or the natural numbers, it has omega, and if a countable ordinal is in X, then it's also a subset of X, right? Because it has, if a countable ordinal is in X, then X has a bijection between that countable ordinal and omega, and then all the points below that countable ordinals are also in. So X intersect omega 1, if X is a countable substructure of H theta, is always transitive. In other words, it's an ordinal. Okay, so I could write Q forces that tau is an element of alpha, where alpha is X intersect omega 1. This is an element of omega 1. Okay, that's another way to think of it. So the semi-generic force is that whenever you have a name for a countable ordinal, then it's actually forced by it that that name gets interpreted by something which is smaller than X intersect omega 1 for your substructure X. Okay. Okay, so this is obviously it's a weakening of the requirement of being X generic, because in X generic we just replace the requirement that it's forced that the name is a name for a countable ordinal to that the name is a name for something in the ground model. Okay, so everything which is proper. I'm sorry, I didn't yet define semi-proper. Sorry. So we defined what was a semi-proper forcing. So P is semi-proper if for a sufficiently big theta, if for all countable substructures X of H theta, countable, let's say P is in X, but never mind. For all P in X intersect P, there is a strengthening which is X semi-proper. There is a Q stronger than P, and Q is X semi-generic. It's the same as the second statement in the characterization of proper forcing, which we sketched. We said a forcing is proper if and only if you have a countable substructure of H theta, theta big enough, I didn't write it down here, and you have a condition in the substructure, then there is a stronger condition which is X generic, and now we just say we want a condition which is X semi-generic. Okay, so it's entirely obvious that if a forcing is proper, then the forcing is semi-proper. Okay. Then there is another definition that P, we say that P preserves stationary subsets. Sometimes you only say that P preserves stationary subsets, which is a little bit misleading because that might sound like you say that the forcing is proper. Okay, so let's add preserving stationary subsets of omega 1 if and only if. What you say is that for all S subsets, now we are only talking about subsets of omega 1. So if you have any subset of omega 1, S stationary, and this implies in V, then S is stationary in the generic extension by P. Okay. So we have 20 more minutes. I wanted to show the following lemma, but the proof I will now omit. It's very easy. I can leave that as an exercise, namely that if P is semi-proper, then P preserves stationary subsets of omega 1. It's actually more or less the same proof as the one which characterizes properness in terms of that you can extend conditions to X generic conditions. It's the very same proof of one direction of that, okay? So what do we have? We have that if a forcing is proper, then it's semi-proper, and if it's semi-proper, then it preserves stationary subsets of omega 1. Another thing you can verify, we can link the whole thing to the concept of CCC forcings, which we saw before in the context of discussing Martin's axiom. So you also have that if P has the CCC, then P is proper. You know what, it just occurs to me that when we discuss the application of Martin's axiom omega 1 to showing that Susan's hypothesis is true, 2 to the aleph 0 is 2 to the aleph 1, I forgot to say that the forcing which we wrote down, the almost disjoint coding forcing, has the countable chain condition. I should have, of course, is important, but it's entirely trivial to verify. Okay. Okay. Okay, so now let me more or less end by stating the forcing axioms which we will discuss in the rest of the series of these talks. So definition. Okay, it's the same thing, it's the same statement as Martin's axiom aleph 1, but for the less restricted classings of forcings, namely the proper forcing, semi-proper, and so on and so on. Okay, so PFA, this is the proper forcing axiom. So this is the statement, right, for all partial orders which are proper, and for all collections D, and now we have to restrict to aleph 1 many dense sets. I mean, by way of definition, I could write down a bigger collection of dense sets, but then the thing becomes inconsistent because already the forcing axiom which I'm about to write down implies that the continuum is aleph 2, as we will see. And so you cannot have even Martin's axiom sub aleph 2, right? Because that implies that the continuum is bigger than aleph 2. But that forcing axiom we are going to write down now implies that the continuum is equal to aleph 2. So you cannot afford to write down anything beyond omega 1 here. That's a key point in contrast to Martin's axiom. So for all P which are proper, and for all collections of dense sets in that forcing of size at most aleph 1, there is a filter G in the ground model, so that G intersect DI is non-empty for all I less than omega 1. Okay, okay, and then the rest of the axioms go the same way. So we have this semi-proper forcing axiom. So same with proper replaced by semi-proper. But it's the same statement, so you consider a semi-proper forcing and you have aleph 1 many dense sets, then you have a filter meeting each of them, and then Martin's maximum is the statement same with stationary set preserving. Replacing proper. Okay. Okay. So I want to end, we have a little bit of time left. I want to just end by stating a characterization of Martin's maximum, which is important for us. It's not important, we could do without, but it's kind of handy to have it and I don't have a chance of proving it. So what I will do is I will give you a reference. Okay, so there is a theorem which I construe as being part of the folklore, but okay, so the following are equivalent. One is, it's actually a way of thinking of Martin's maximum, a nice way of thinking of Martin's maximum. Okay, so the second statement is the following. You could even define Martin's maximum in that way because it's equivalent for all A in V. This is just your favorite set, right? You could think of it as a model, for instance, that it makes some more sense, but it's okay. It's your favorite set. And for all forcings, stationary set preserving, right? I mean, by which I mean that you preserve stationary subsets of omega 1, and you fix a sigma 1 formula. If for all phi, which is a sigma 1 formula, if it's forced that the sigma 1 fact is true about A, okay, then you cannot really say that phi of A is already true in the ground model. For instance, the forcing to collapse omega 2 to omega 1, this is an easy example. The forcing to collapse omega 2 to omega 1 preserves stationary sets. It's even proper. Okay, so there is a statement, there is a sigma 1 statement saying that there is a surjection from omega 1 onto omega 2. So you can force it to be true even by a proper forcing, but it's not going to be true in the ground model. Okay, so we cannot simply say that then V thinks that phi of A holds true. This doesn't work. But what works is the following. Okay, then it's easier to write it down in terms of models. Okay, so let's do it. So let me replace the A by a model. For all models, what's going on by models? M in V. So when I write models, what I mean is a model of arbitrary size, but the arity of the model should be at most Aleph1. So there should be at most Aleph1 many relations. Okay, so the signature has size at most Aleph1. Okay. So then there is a J, an elementary embedding from some M bar into M, an elementary embedding, so that the cardinality, so it has small cardinality, is at most Aleph1. So I allow a signature of size Aleph1. So in particular, I could have constants for my favorite Aleph1 many elements of the model. And then if I have an elementary embedding J from some M bar into M, M bar is in the same signature, then these Aleph1 many elements of M have to be in the range, right? So I can make sure that certain points are in the range of the map. In particular, I could make sure, for instance, if M is a large transitive thing, that omega 1 is a subset of M bar and is an element of M bar. Okay, so I would have a critical point if M is transitive, which maps the pre-image of omega 2 to omega 2. Okay, so I say that there is a J so that V thinks phi of m bar. Okay. So this actually turns out to be equivalent to Martin's maximum. The direction 2 to 1 is very easy. That's an exercise. Namely, you have to show that if you have a stationary set preserving forcing and you have L(1) many dense sets, then there is a filter which meets them all. Well, you certainly get a filter which meets them all by just forcing. Right? In the forcing extension, it's true. But the fact that, that there is a filter which meets all of these dense sets is a sigma-1 statement in which parameter? It's just in the enumeration of the L(1) many dense sets. So you can take your model just basically as the collection of these L(1) many dense sets. And then if you see the conclusion, you have this J, and which by the way is supposed to exist in V, and the statement, the sigma-1 statement in V. So you have this substructure for which you have a generic. You have a substructure of size L(1) for which you have a generic, and you can pull it up and you get a filter which meets all the given dense sets. So the direction 2 implies 1 is very easy, and 1 implies 2 is a little bit more delicate, but it's not hard. It's so the proof is given in a paper by Ben Claverie and myself, and it is called Fudan's axiom star bounded forcing axioms and precipitous ideals on omega-1. And it's published in the Journal of Symbolic Logic, 77, 2014, pages 231 to 261, and is theorem 3.1 there. It's easy, so you might want to take a look. Okay. Now,
Ralf,
yes.
There's an A in the if clause.
Yes, I also want to thank you very much. I started with the A and then I replaced it by a model. Yes, thanks. So this is also the model. Thank you.
Mm-hmm.
Okay. So I also wanted to mention Martin's maximum double plus, but I think there will be another occasion where we. So let me just say it without writing it down, and then we are done for today. So there is a slight strengthening of Martin's maximum, which is called Martin's maximum double plus. It's the same statement like Martin's maximum, except for you also say that in addition, I have a collection of L(1) many names for stationary sets. And then I want the filter to interpret these names by actual stationary sets. And equivalently, I can say that similarly as here, I can say that MM double plus is equivalent to the statement as the statement 2 here. But when I say that the formula is sigma-1, I allow a predicate for the non-stationary ideal as a predicate in the formula. Okay, but we will have a chance to discuss this a bit further. Okay, so we have 5 more minutes, but I would say this is a good place to stop. And maybe I could say that we just discussed that we start out an hour earlier tomorrow and make 15 minutes break instead of half an hour, but there will be an email about this.
Yes. Thank you, Professor Ralf Schindler.
Okay, thank you.
Do we have any questions?